Hello and welcome to Lesson 3 of Computer Systems for National 5 Computing Science. Today we're looking at the description of floating point representation. It's for positive real numbers using terms like mantissa and exponent. I've got a presentation for you, and we are going to learn all these things, even though I think this last one might be for higher computing science only, but it used to be at National 5 level, so I'm keeping it in just in case it creeps back into the National 5 course. So we are going to describe how computers represent real numbers, and we'll be able to state the two parts of a floating point number, and we'll describe the effect of changing these two parts, changing the bits used for each part. Before we get into how computers use floating point numbers, let's talk about scientific notation. Now, this isn't exactly scientific notation. As you'll see, it starts with a 0 instead of the most significant digit, but let's look at it anyway. So in a science textbook, you would never normally see sentences such as the half-life of selenium is 97 quintillion, whatever this number is, quintillion, sextillion, I don't know, this many years. They would never write out all these zeros. What you would see is the scientific notation where you take a decimal number and you multiply it by 10 to a certain power. And that represents how many decimal places that point here, the decimal point, has been shifted. So computers use this kind of system. They use this idea. Instead of having all these zeros after the 1, it would just be 0.101011 times 2, because it's binary. And then this power number here, which if you do your binary conversion, it's a 1, 2, 4, 8, 16. So that's 17. This represents 17. So this decimal point here, or binary point, the floating point, has moved 1, 2, 3, 4, 5, 6, 17 places. Okay, so it would have been here, but now it's moved 17 places to the front of it. And regardless of whether you're doing it in binary or whether it's in denary, there are two parts to these numbers. We've got the first part, which is the 0.97, the decimal part, the part with the significant digits, and the second part, which has the power number in it. Technically, it's three parts, because this one here, this is the base, the 10, but the power number is one we're interested in. And these have names. These parts have names. The first part is known as the mantissa. There it is, mantissa. And the second part is the exponent. I don't know if you've ever done a massive calculation on a calculator, and it sometimes comes up with a number like this, 0.97, and then an E, and then a number. E stands for exponent, so that means times 10 to the power of the exponent. So we've got the mantissa and the exponent. Now, I think that you only need to know about the mantissa and the exponent, and to be able to identify these two parts. I don't think you'll need to know the rest, but just in case, let's learn it. So if you have a floating point number such as 0.97 times 10 to the 20, that's not a very accurate or precise number. If you had more digits to represent the mantissa, right, instead of the 2 digits, or the 0 point and then 2 digits, we've got all of these digits. This is much more precise. So increasing the size of the mantissa has increased the precision of the number. Mantissa relates to precision. When it comes to the exponent, you can see that increasing the number of digits for the exponent, the size of the exponent, we have a wider range of numbers. Now, this it's not a very intuitive way of demonstrating this. So for example, if you had 2 digits for the exponent, if you're going 10 to the power of, the range you've got if you've got 2 digits is you can go from 0, 0, if it's positive, all the way up to 10 to the power of 99. Now that's a pretty enormous number, to be honest. Any number times 10 to the power of 99 is going to be large. But if you had 3 digits for your exponent, if you can do 10 to the power of, 0, 0, 0 is still your lowest number. That's still the lowest number, but it can go all the way up to 10 to the power of 999. Now, I think you'll agree that the range of numbers that you can represent here has increased significantly just by adding one extra digit here. So the size of the exponent, it changes the range of possible numbers. This is a much larger range, this 3-digit variety here. Oh yes. But as I said, that should not creep into the National 5 course. I'm only including it because way back, many years ago, it used to be part of the National 5 level courses. But what you should expect to see is a question like this. It says the value 195 would be stored in a computer system using floating point representation as shown below. We've got 0.195 times 10 to the 3. Your job would be to identify the mantissa and the exponent. So what's the mantissa? Now, it's important to note that the mantissa is just the significant digits. The computer system cannot store binary points or decimal points, and it would just ignore the 0 as well. So I'm just scrubbing that out. It would ignore that. And it's also important to note that the 10 is not part of the exponent. That's the base. All about the base. So the 10 is out of there as well. So the mantissa is 195. The exponent is 3. And we can see that here in the marking scheme. The mantissa is 195. The exponent is 3. In the notes here, it also says award marks if either answer is converted to binary. I don't know why anyone would do that, but if you wanted to waste time, you could and still get the marks. Another question that's come up in a past paper, describe how a real number is stored in a computer's memory. 2 marks, so that should be telling you there are 2 things you should be mentioning. What 2 things do we know that relate to real numbers? The mantissa and the exponent. Haha, there you go. If you said floating point as floating point or using floating point representation, that only gets you 1 mark, as you can see there. Now this is a past paper question. Obviously the questions change every year, so you can't always predict exactly what the question is or what the marking scheme will say. But as long as you remember what a mantissa and an exponent is, you'll be fine. So there you go, we can do all the things you've seen here. I hope you've enjoyed it, and I'll see you in the next one.